Okay, everybody, welcome back. In this video, we're going to be discussing Unit 1, Section 12 for AP Calculus, confirming continuity over an interval. Okay, so not a lot of examples or a lot of fresh material here compared to things we've seen. Let's start here. The definition of continuity on an interval. It says a function is continuous on an interval if the function is continuous at each point on the interval. It seems to make sense. I mean, if we were looking at a function, f of x from 2 to 4, and if the function is continuous everywhere in that interval, at every point in that interval, then we will say that it's continuous on that interval. Excuse me. Now this is the next one here is where it throws some people for a loop. A continuous function is one that is continuous at every point of its domain. Notice that is different from saying that a continuous function is one that is continuous at every point. Well, at every point. That phrase of its domain is a very noticeable distinction that enables us to say that some functions are continuous that maybe when you look at them, they violate the intuitive definition of continuity that we started with when we first started talking about continuity. So next what we're going to do is we're going to look at, these are 6 types of functions that are always all continuous because they are continuous at every point in their domain. The first type, polynomials, that one shouldn't come as any kind of surprise. If we graph a polynomial y equals x squared minus 5x plus 6, boom, we should already have a pretty good idea that, with this parabola, it's continuous at every point, not just of its domain, but this is one that is continuous everywhere, and all polynomials are continuous everywhere. So, no matter what polynomial we choose, it's going to be continuous everywhere, and therefore it's going to be continuous at every point of its domain. Rational functions. Now those are a little different for us here. Suppose I take the rational function y equals x squared plus 7x plus 10 over x squared, let's do minus 4. Now, this function, if you look at it, you can see a discontinuity right here, and that discontinuity is happening at x equals 2. Okay? You can also see, actually you can't see, but you could see if you found the value, there's also discontinuity over here. See if I can get on it there. At negative 2, there's a hole in the graph. Even though you can't easily see it, there is a hole in the graph. So this graph indeed has 2 discontinuities. However, when we define rational functions, we define their domain as everywhere where the denominator is not equal to 0, and x equals negative 2 and x equals positive 2 are not in the domain of this function. So this is considered a continuous function because it is continuous at every point in its domain. Okay. Next on the docket, root functions, third root, fifth root, second root. The odd roots aren't as much of an issue for us here maybe as the even roots are. Suppose I take, let's see, where are my roots? I always forget where things are. Maybe I don't even have roots. Oh, there it is, nth root. So suppose I want to take the third root of x plus 5. No problem with this function at all. it appears to be continuous at every single value of x, and indeed it is, and so it's continuous at every value in its domain. However, if we go to the fourth root of same function inside there, we notice that the function comes to an end here at -5. So the function isn't continuous over here. This function's not continuous at -15, but the function is still considered a continuous function because -15 is defined as not being in the domain of this function. The domain of this function is x is greater than or equal to -5. And all values of x greater than or equal to -5, the function is continuous at all of those values. Okay. What else do we got up here? Oh boy, I hate when I click on the wrong thing. Trigonometric functions. The sine and the cosine, it's pretty obvious and clear to us that that's the case. But the other trig functions, not necessarily as clear and obvious. If I type in y equals tangent of x, this function has a ton of discontinuities. It's just that all of those discontinuities are at points that are excluded from the domain. So again, we consider all 6 trig functions continuous because they are continuous everywhere in their domain. So there's a distinction here that you want to be aware of, the continuity on an interval. If I looked at this function that I just graphed, the tangent function, if I look at it and ask, is this function continuous on the interval from 0 to 10? The answer is no. However, is the tangent function continuous? Yes, because it's continuous everywhere in its domain. And that's an ugly distinction that, some people struggle with. Exponential functions, logarithmic functions, again, I could graph those as well, and you'd see something pretty similar to what we saw when we took the fourth root of x up here. We've got a function that, well, not with the exponentials, but with the logarithmics, we've got a function where there are x values that are not in the domain of that function, but the functions are still considered continuous. So these are all functions that are continuous. Okay? Sliding down to the bottom here, with the caveat that a function's continuous at every point in its domain. That takes care of the discontinuities in rational functions and the trig functions. Are there actually functions that aren't continuous? Can we write or draw some functions that aren't continuous in their domain below? So let's start with the first question. Are there actually functions that aren't continuous? Yes. Many functions aren't continuous. The prime example comes to us from piecewise defined functions. So for instance, can I draw some? Okay, here's a function that is not continuous. Okay, and it's not continuous on its domain because at this x value, the function exists, but there's a discontinuity. Another popular one that you might remember from a previous course. Ye old step function, where we've got all of these discontinuities, and the function exists. The domain of this actual function is from -infinity to infinity, but there are places in there where there are discontinuities. And I could write a function that's discontinuous. The easiest way, like I said, is to write it as a piecewise defined function. Suppose f of x is equal to sine of x over x for x not equal to 0, and it's equal to 5. at x equals 0. This function is not continuous everywhere on its domain, and so it's not a continuous function. Okay, that's all for this video and all the information from this lesson. For those of you who are in my class, there's a bunch of practice problems and also my AP assignment that you want to be doing before the next time I see you. That's going to be it for this video. Next time we'll be back with section 1.13. We're getting close to the end of Unit 1, so let's keep steaming along. Have a great day, everybody, and I'll see you again next time.